Okay, so this is I recording on to the crash course on nuclear chemistry. So week 11 is I'm going to focus on the nuclear chemistry, and there is a nuclear chemistry one, uh, which is the one of the sections in the YouTube, and this is a more second version. But I having a same common portion that I'm sharing with you guys. So this is a first thing that I wanted to talk to you about. You might heard about alpha, beta, gamma ray. This is just a term that it is in a way, to my mind, is a very strange term because of the historical reason. The Rutherford, who is a Nobel Prize winner at and he studied the structure of atoms and so on. And in his mind, he find out if you have this, he can generate rays of particles, and some particles are withdrawn to the negative potential. Some of them are withdrawn to the positive potential. So this is in a vacuum tube, and then he put it up to the positive terminal and negative terminal. And the first one, that's why he called alpha. Okay, I didn't at that time. He doesn't even have an idea about what it was. It's just the one that being attracted to the negative terminal. So it must have a plus charges. And later he find out it is an atomic number 4 with a mass of 4, atomic number 2, mass of 4. That's a helium, and as you know, it's not 2, it's not plus, it's a 2 plus. So it has a name. But just historically, the first one he did is an alpha, and second one he did is a beta, and that one is, if somebody did this experiment, probably the person would never call this as a beta, would just call it an electron, but at that time we just called it a beta because it's a second system that he worked on, and then it was attracted to the positive terminal. So later you find that this is a beta ray, and beta ray has a negative charge, and then has almost no mass, and then that's the property of the beta ray. The third one, alpha, beta, gamma, right? The third one is a gamma ray. Gamma ray is actually nothing but is an electromagnetic wave. This is probably the first equation that we visit in Chem 1 class, right? Anything that electromagnetic field oscillation, electromagnetic wave has a frequency with a Planck constant. That's a light, right? Gamma ray is a part of the electromagnetic wave, which is we also call quote unquote light. Right? So that's the you just have to know the different notations, and this is happening sometimes. Alpha particles, beta particles can come out, and the gamma ray is also can come out from the nuclear reaction. And there's a little bit more, and then people use in this area, they use a nuclear symbol. So let me slide it to the second section, which is I made this copy of the classroom slide, and it's just extra, the redundant one, but just want to emphasize once more the proton, neutron, electron. Those are the most common one. And then, proton has a mass 1, and the mass also 1. The proton number is 1, and the mass is 1, right? So that's why he used this one, and then the proton, there's a mass 1. Whereas the electron is opposite charge of proton, so there's a negative 1, has almost no mass. And the neutron has no proton, but mass is closer to, it is very similar to the proton, so it's just a 1. Either neutron or proton, you count it as a 1, right? And so these are the notations that people use. Sometimes a proton, we can just use it as using the symbol hydrogen. And then comes an alpha, right? Alpha is, we use an alpha, as you know. This is a notation that one, and I just use that 2 plus 4 and 2. And these alpha 2 plus charges, they just exist as a nuclei, 2 plus particles in the vacuum, but when you expose, they're going to grab the electrons from wherever possible to be a very happy helium. So sometimes you can write it this way, sometimes you can write it that way, and depending on who's writing it, but essentially what's key here is helium with the atomic mass number 4 is what is shown up there. Okay, and then the beta, beta is beta, right? The beta is, it's just nothing but electron. So this is what most people would love to write, and I don't think this is even common to write this way. And then there is something called a positron, which is an opposite side of the beta. So they call it beta plus, and so this is a commonly known. This is well, questionable, but most people write it either beta or beta plus, where beta means an electron. Beta plus is something that has an opposite charge of the electron but has no mass, right? So this is that's the positron that they show you. This notation is not so common, but make sure that you understand this notation when they are using it. So there are kind of the different ways to people write. Sometimes they write it as an emission. Sometimes they write it as capture. Okay, when they say capture means the reaction happens, you need to use this one, right? So this one need an electron for the nuclear reaction. That's called an electron capture. That's a one common reaction, nuclear reaction. Whereas an emission is, it happens after, right? After the reaction, this is coming out and this is coming out. Funny that I just told you that this is not being well used. So it's actually, I prefer you guys to use this way. I prefer you guys using positron plus 1 and almost no mass. So you can write it that way. I don't know. Even let me be bold enough to just scratch that off, right? So that's the one that most people commonly use that, and that's a notation. And this is an answer key that I just take it out from your discussion problem number 1, which is different types of radioactive decay mode. In my crash course, nuclear chemistry number 1, actually, I went up a little bit more about that, explaining this. But this one, you can see that the most important guiding map that I wanted to do is, I'm going to color this, okay, 94. And then what you need to do is 94, they just give it to you. Then you need to turn it on. Okay, so 94 is, you look for the 94. That's, where is the 94? Okay. These numbers are so small. This is a 94. That's the 94, right? So that's a 94. You can see that. So atomic number and the plutonium, those symbols are the same. So make sure that, in a way, this is a redundant. Okay. Sometimes that's why sometimes people do not write when they say PU, they don't write 94 on the side. But make sure that this is go by always number of protons define what kind of atom you're defining it to. And so make sure that you have this balances out. And then the one on the top is it's a number of protons and the neutrons. So plutonium, and then now you can see that, okay, what about if you have an alpha particle emitted, and then you're going to lose 2 protons, so you're going to get 92, and you look at the periodic table, you find that that's a uranium. So that's how you do. Okay, so you go and look up the 90. This is a plutonium 94, and the 92 is a uranium. So you look at that, and then you find out the symbol, putting it up, and then you kind of balance it out. 242 should be 4. So if you subtract 4 from 242, that's a 238. So that's the number of proton and neutron in the uranium in this alpha ray emissions and so on. But it's always a remember, the magnesium that you can see from the periodic table is number of proton is 12, right? And then this is a case where, okay, what about if you emit the electrons and has no mass, right? Electron is this case, and in this case, and then 12, and you actually you need to generate more protons by losing this. So it's actually one of the by doing so, your proton numbers actually goes up, and 13, and then you look up your periodic table, and then there's an aluminum. So that's a kind of logical sequences. Okay, so the 13 before it was a magnesium, and one more proton is on aluminum. So that's the number, and that's what you guys can find out. And so you fill that up, and then you kind of balance the number of atomic mass gain on the top. The same thing here, silicon 14, and then this is a positron emission, and so now it's a 14 minus 1, 13. Look up the periodic table, aluminum, and finish the rest. And this one, if you look at this, this reaction was electron was used as a part of the reactant, right? So this is in a way, this is what they call electron capture. That's a term. Whereas this is the emission, right? Alpha emission, beta emission, beta plus emission, right? And positron emission. You can say that, but this is an electron capture, and you guys can see that as long as you know how to do the balance and so on. And so this is an 18, and then they got the electrons, so then you can reduce the number of protons in the electron capture reaction, and that will comes in later. Okay, so make sure that you go and then get yourself used to it. I mean, the plutonium is a big in the nuclear chemistry, uranium, because of the we have a very unfortunate things happened during the World War II, and this is really the key component that generates a lot of energies, because neutrons and the protons are having a different mass, and when they are combined, and then when they are kind of when they essentially the nuclear reaction to change, and there is atomic mass is changing, and then that is shown up as a form of energy. So that's what we are using it for the nuclear power plant, so it's peacefully we can use that as well. Okay, so the lecture number 2 on the nuclear chemistry recap, I am going to more focus on what is called the half-life. Okay, half-life. Let me make it this way. So what is half-life? Half-life is something that has first of all, we are using the symbol T half. So time to take. Okay, so half-life is time. It's a time. Okay, it's a time T to make your concentration A equal half of your original concentration. So that is the meaning of the half-life. Okay, so what that means is this is your initial mass. So this is what we call the A naught, initial concentration. This is we covered this in the reaction kinetics, and this is essentially the same thing. And this is essentially 50% from the original mass. That's what we call the half A naught. So I just got this one from the lecture slide. So this is a time, right? This is a time, and in their way it's actually multiples of half-lives, but this is what they say. Oh, this is a 1 then. What that means is it's a 1 times half-life. Okay, so 1. If you add the half-life, your concentration gets to the half. Here's I want to get to the math component of this, so let me do the math. The thing is, you don't have to remember the math equation, because let me show you this. So in your exam reference sheet, you can find out, okay, you have to know what that means though. Okay, that's a 0th order, this is a 1st order, That's a second order. This is the half-life equation for the first order. And we are dealing with a first order equation for the radioactive decay. The radioactive decay is first order decay reaction. Okay? And the notation that people write is A goes to product, and then remember dt dA is a KT. And then you solve this equation. So they put it minus there, and if you solve this equation, you'll find out A over A naught is minus KT natural log. So that's the equation. If you look at this equation and compare the equation that you see now, that's the same equation. Okay? This equation that you in the reference sheet is same as the equation shown up here. And I like this equation version number 1 because it shows that concentration ratio and the time it takes, and then the rate constant K is right there. Another equation form that you can flip this one is A is A naught e to the minus exponential to the KT. So that's the same equation, just flip it the other way around, and those are the equations that I like to use. And then what did we say about half-life, right? Half-life, well, T half, is when your A becomes half of A naught, right? So using that notation, I can plug that in, and then this half naught means ln half of A naught, and the A naught becomes minus K T half, right? So that's the notation that I can have. So this one becomes actually minus ln 2, and if you combine this together, therefore you can find out half-life is ln 2 divided by K. Okay, so that's the relationship of the half-life. Because the half-life is something that easy to quantify, people can measure this as a function of the time, right? For example, here, this is actually one of the questions in the radon. And the radon, this is a initial concentration, and they can do the experiment and then say, okay, 1 million, half of the 1 million is right there, and then that's the one, and so that is your half-life, right? So they can measure the half-life very easily. So half-life is something that you can measure easily, and once you know the half-life is also ln 2 over K, so therefore you can know your rate constant, which is I guess ln 2 over 1, which is just a ln 2, and the unit is per minute. Okay, so you can find out. I don't know what was the question here. Determine the half-life. So you look at the A naught going to the half here, and that's the time, and that's 1 minute. So that's 1 minute is the answer for this kind of a question. But this time I wanted to spend the time to show how this half-life equation can be derived, because there is a previous exam problem, which is actually I'm going to solve it right now today in the remaining discussion session, and about how the concept of the half-life is being used, and I can talk to you about this. Okay, so let me stop the recording now.